Good morning, everybody. Today, actually, I'm going to discuss the background of quantum mechanics. This part is not essential for net purpose, but for it will help you to understand the quantum mechanics, how quantum mechanics is started, and why it is developed, and why it is necessary to develop quantum mechanics. So everything's we for understanding of everything, we have to understand the background of quantum mechanics, why it is so necessary. It will help you to understand the remaining part of the physics, and specifically quantum mechanics is very essential for analyzing the nature of microscopic particle in microscopic domain. Okay. And what happened before in 19th century, that's what I'm going to discuss. So in 19th century, what happened, scientists thought, in 19th century scientists thought that three part of physics, classical, which is also known as a classical physics, which include the Newtonian classical mechanics and electrodynamics, Maxwell theory of electromagnetism, and thermodynamics. These three classical part will explain whole physical phenomenon that is in 19th century. 19th century. So what happened at the end of 19th century? At the end of 19th century, that I mean at the turn of 20th century, this classical physics faces serious challenge in explaining few phenomena. So challenge, two important challenges that the classical physics face. One is relativistic domain, relativistic domain. Two is microscopic domain. The classical physics face this challenge. The fail in major challenge, that means they are totally fail into domain classical physics at the turn of 20th century, just beginning of 20th century. So in 1900, what happened? In 1905, Einstein relativity theory was introduced. In order to overcome this difficulty, in 1905, Einstein provided a relativity theory in 1905. This theory shows that classical physics, I mean Newtonian physics, is valid only only low velocity particle. I means whenever particle moves at very high velocity, comparable to the velocity of light, then classical physics totally fail to explain the dynamic nature of the particle. In that case, relativistic dynamics is more significant. That means Newtonian mechanics is a special case of relativity theory. Whole dynamics, whole natural phenomenon and dynamics of particle, whether it is subatomic or atomic, microscopic particle, everything we can be explained using the relativity theory. But Newtonian mechanics is a special case of relativity. So in the second case, what happened in microscopic domain? So initially thought that every physical phenomenon can be explained by the classical theory. But at the turning of 20th century, what happened? Many experimental technique had been developed, and this experimental setup or experimental technique enables the scientists to examine the nature and behavior of atomic and subatomic particles. And it is experimentally seen that classical physics measurably fail in explaining their dynamic nature, in quantitatively as well as quantitatively fail in twofold. Then scientists thought that there must be new mechanics that to be adopted, which is later named as a quantum mechanics. Okay. This is the major turning point from where we had to think about the new mechanics. So first breakthrough comes in 1900. Breakthrough, Planck, Planck quantization law, that is in 1900, which is known as a Planck's blackbody theory or Planck quantization law. We often know as Planck quantization law. So first vector comes in 1900, that is provided by Max Planck, which is also known as the quantization of energy. Okay, Planck provide the quantization of energy, and taking the concept of quantization of energy, Planck successfully explained the blackbody radiation theory, and this result obtained by Planck is accurately matched with experimental data, and it overcome the difficulty in explaining the blackbody radiation spectrum. So what is a Planck concept? Planck told that suppose this is radiation source, this is a matter. So initially classical thermodynamics law, Rayleigh-Jeal law, Wien-law told that exchange of energy between source of radiation and matter take place in continuous manner. It is a continuous process. Exchange of energy between source and matter is exchange. I means whenever you give it a radiation on a particular object, so there will be exchange of energy from the source to matter. So this exchange of energy, transformation of energy from source to matter is a continuous process. Okay, but according to Planck, this exchange of energy between radiation source and matter is not a continuous process. It is in discrete packet of energy. So what do we mean by that? E equal to h nu, n h nu. N is the integer. It is start from 0, 1, 2, 3 like that. It goes to infinity. So it will give energy h nu 0, 0, then h nu, then twice h nu, like that. It's a discrete energy. First, source will give, radiation source will give 0 energy, then h nu energy, then twice h nu energy, then thrice h nu. This way, exchange of energy take place according to Planck quantization concept. Okay, and this Planck concept successfully overcome the difficulty as faced by classical thermodynamics law, as we have already heard about Rayleigh-Jeal law, Wien law, which is unable to explain the whole blackbody spectrum. Okay, this problem was overcome by Max Planck. That is why we often know Planck blackbody radiation. We will discuss later in detail. Okay, this is just background why quantum mechanics start. That's why I briefly explain. So after this theory, Einstein photoelectric effect. Einstein photoelectric effect. So what happened? Taking the concept of Planck quantization of energy, which evidence that electromagnetic radiation is a discrete packet of energy which is known as tiny particle, which is known as a photon. That means electromagnetic wave is composed of large number of photons with energy h nu 0, twice h nu, thrice h nu, like that. So blackbody radiation is a particular aspect of radiation. It is not wave aspect. Okay. So taking the concept of Planck quantization energy, Einstein provided a powerful explanation of photoelectric effect. What actually photoelectric effect? Einstein told that whenever we allow electromagnetic radiation or photon particle on a metal surface, so there is a 1-to-1 interaction take place. That means one photon will interact with one electron of the metal surface, and electron will absorb whole energy from h nu and overcome the threshold energy and come out from the metal surface. So this is what happened in photoelectric effect. This is h nu. This is electron will come out, okay, with velocity v. Suppose h nu is a photon energy. So one photon energy fall on the metal surface, electron on the metal surface will interact with the photon energy, H nu, and some portion of energy will use to overcome the stopping potential, or sorry, not stopping, threshold energy or work function of the metal, finally will come out. And this theory, Einstein theory, accurately explained the emission of electron from the metal surface. So what indirectly we can say, Einstein also provided powerful experimental verification of Planck quantization of energy. So Einstein photoelectric effect gives the particle aspect of radiation. So photon here is electromagnetic here, considering the photoelectric effect is the particle behavior. It explains the particle behavior of the photon, not wave behavior of radiation. Okay. This is the photoelectric effect. After these two powerful explanation, Planck and Einstein theory, seminal breakthroughs one by one come into play in physics. So first breakthrough in this physics occur whenever Rutherford provided Rutherford model that verify the discovery of nucleus. Okay, Rutherford model that provide the discovery of nucleus in 1900. One is Rutherford model. That is in 1911. Rutherford provided theory model that discovered the existence of nucleus in 1911. That is after this experiment, two photoelectric effect and black body radiation, Planck theory and photoelectric effect. Number two, Bohrs theory. 1913. So taking the what happened, you see, in chronological order you try to focus why and how. So taking the concept of Planck and as well as Einstein, and considering the model of Rutherford, Bohr's atomic model of Rutherford, Bohr's in 1900 provided model which is often known as a Bohrs model. So Bohrs model tells that atom can stay any discrete energy level. Okay, interaction of energy with matter take place, or emission or absorption take place in terms of a discrete amount of energy. Okay, and Bohr's theory provided powerful explanation of various spectra like Lyman series, Balmer series, Passenberg series, different spectra we have already studied. Okay, this Bohr's theory also enable us to analyze the atomic stability and spectroscopic properties of particle. Spectroscopy we have studied. Bohr's theory gives a new direction to analyze the spectroscopy, to analyze the atomic stability. But what is the limitation in Bohr's theory is that the most of the assumption in Bohr's theory does not have any mathematical background. That means Bohr hypothetically assume many assumptions that does not have theoretical background, and that is why during that time Bohr's theory was highly criticized, and Bohr's theory successfully partially success in explaining various phenomena. But mostly Bohr's theory is a mixture of both classical and quantum mechanics. Later we will discuss. And further, Bohr's theory cannot give selection of intensity rule. Okay. Okay. And after that is in 1930. After third breakthrough comes. In Compton effect, 1923. So, in 1923, Compton provided powerful conclusive experimentally confirmatory experiment, which is known as a Compton effect. And what happens if a X-ray photon is allowed to fall on a free electron of atom? Free electron of atom means, free electron of atom means it is the outermost shell electron. Then shift of energy or frequency take place. This Compton effect clearly verify the particle aspect of radiation. So in Compton effect, he considered X-ray photon of high energy X-ray photon allowed to fall on a free electron of atom, or electron in the atoms, which is the outermost shell electron. Most outermost shell electron is known as a free electron, and because of interaction of electromagnetic radiation and outermost electron, the shifting of frequency take place. Okay, this shifting, suppose Compton shift, we often know Compton shift is by M.C 1 minus cos theta. Cos theta is the theta is the scattering angle. So this Compton experiment evinces the particle behavior of the radiation, and this experiment photon is considered as a particle. Okay, that is in 1923. What we can say, Planck, Einstein, Bohr, Compton. What we can say, Planck, Einstein, Bohr, Compton. These experiments are already evidence, have already given. So these 4 experiments establish the many things. One, quantization rule, and another thing, the particle aspect of radiation. I means this experiment proved that electromagnetic radiation is a composed of bit of energy or a tiny particle, which is known as a photon, and photon can behave as a particle in addition to wave nature. So this experiment behavior establish the particle behavior of the radiation. Particle behavior of radiation. Okay. And if we know that this experiment establishes the particle behavior, how can you establish the wave behavior of radiation? Wave behavior of radiation can be obtained from interference and diffraction pattern and polarization pattern. We already know in wave optics, it is not geometrical optics. In wave optics, light is an electromagnetic wave. It can show interference, diffraction, polarization. That means light behaves as a wave. Okay, but this experiment evidence that wave, radiation or photon particle can behave as a particle. So up to this, so what we can establish, radiation behave as a particle as well as wave. Okay. Then what happened? In the same year, in the same year, 1923, if radiation can behave as a wave as well as particle, then in 1923, De Boer provided powerful theory which tell that any particle, any metal particle, including photon is not metal particle, but it is, later this equation is generalized. Metal particle also have dual behavior. So dual behavior means metal particle can also behave as a wave, as a particle. So that is why he provided it with equation which is known as a P is by mv. What does it mean? So he told that De Broglie suggested whenever material particle moves, wave is associated with it. Okay, and wavelength of the wave is given by this. But whenever mass of the particle is very, very high, means macroscopic particle like me, suppose myself, in comparison to the electron proton, my mass is very, very high. So in case of macroscopic particle like me, object, the wavelength is insignificant, then the particle behavior is more significant. Wave behavior is negligible. But in microscopic particle, so they can behave as a wave, they can behave as a particle. Their wave nature and particle nature is not insignificant. But whenever you analyze a particle, you can analyze either particle nature or wave nature, but you cannot analyze both nature at the same time. Or you can say that there is no such experiment has been developed so far through which we can analyze both property at the same time. You can say like this also. This is Bohr's theory, but these de Bohr relations. Okay, later this equation is generalized as for the wavelength associated with any particle. Any particle means it may be material particle, it may be non-material particle. Non-material particle like photons, and material particle electron, proton, like that. Okay, in 1927, that is in 19, Davison and Garma explained 1927, and remember in 1929, Bohrs was awarded Nobel Prize in Physics for this development also. And in 1927, the experimental verification of wave aspect of particle was done by Davison and Gamma. That means Davison Gamma in 1900 shows that any material particle, for example electron, they consider electron, can show the wave property. What is the wave property? If any particle can show the interference pattern or diffraction pattern or polarization pattern, then we can evince that this particle behaves as a wave. So what then in Davison Gamma experiment they did, instead of photon they consider electron. Photon particle they consider electron, and they try to extract the output. What actually they get at the output? They at the output in the experiment they get interference pattern. Okay, if interference pattern is obtained from electron and mechanism of electron involved in the experiment, then what we can understand that electron behave as a wave. So in 1927, and for which they commonly awarded Nobel Prize also in 1939. Okay, this is theoretical, this is experimental, this is Bohr's theory. Okay. So now what happened? First quantum, and most problem is that Bohr told that de Broglie told that wave associated with the metal particle. But what type of wave associated with the metal particle, de Broglie cannot say. So in order to solve problem, they then start thinking to develop new equation toward quantum mechanics. So quantum mechanical equation has to be developed, solution of which equation give the wave like Newtonian equation. If we solve Newtonian equation, we know the dynamic of the particle. Similarly, some equation must be developed, solution of which give the nature of wave nature of the particle. De Broglie suggests that wave is associated with it. What type of wave associated with the particle, De Broglie cannot say. Okay. So in 1925, so after all this experiment, in 1905, first quantum mechanical postulate was formulation is developed. In 1925, first quantum mechanical formulation was adopted by Heisenberg. Heisenberg provided the first quantum mechanical formulation in 1925. That is known as a matrix mechanics. This matrix mechanics is valid only for discrete system, not for continuous system. And after 1 year, in 1926, Schrödinger provided wave mechanics. That's what we are going to study in the later course. Understanding of this part is very essential in order to understand the rest of the quantum mechanical part. If we understand the basic background and requirement and postulate of quantum mechanics, then we can understand physics quantum mechanical part very efficiently, and it is necessary and essential too. Okay. In 1926, Schrödinger developed wave mechanics. It is for continuous system, but these two are interchangeable. Means sometimes wave mechanics you can transform to the matrix mechanics, or matrix mechanics you can transform to the wave mechanics under suitable condition. Okay, that's what we are going to discuss in the next chapter, next class. Okay, but we know in Schrödinger or matrix mechanics, any particle like me, you consider me as a particle, but in quantum mechanics, this particle is not specified by Anil Hazarika. Okay, this particle, suppose me, myself, is considered as a wave function. Any particle is represented by a wave function in quantum mechanics. Suppose a quantum mechanics electron is not specified in quantum mechanics as an electron. Electron is represented by a wave function. Okay, in quantum mechanics, electron is represented as suppose phi, represented by the wave function. The nature of the wave function, we will get the solution from the Schrödinger equation. That's what we are going to discuss. If we solve Schrödinger equation, you will get a wave. Okay, any differential equation. If you solve any differential equation, you will get a solution. If you plot this solution, you will get a wave also. Okay, and from the solution of Schrödinger equation, you will get a wave function solution. That solution is known as a wave function. But this wave function represents the particle. Wave function represents the particle, and from this wave function you can extract all necessary information, state, energy, everything. You can extract the information. What is the moral of the story is that any particle in quantum mechanics represented by the wave function, not by name, something, other nature. Okay, this wave function does not have a physical meaning. This wave function does not have a physical meaning. So in order to describe the physical meaning of this wave function, in 1927, Max Born probabilities interpretation. So in order to explain the physical nature of the wave function and meaningful explanation of wave function, Max Born in 1927 provide a probabilistic interpretation. He told that the wave function does not have a physical meaning, but square of the wave function, this wave function, no physical meaning, but the square of the wave function, square modulus, it is square modulus, or you can write like this, dot psi has the physical meaning, and it will represent probability of finding the particle within the specified limit. Okay, in 1927. That is in 1900. That is we also know probabilistic interpretation of the wave function. That is given by Max Born. Okay, 1928. Dirac. And one thing I like to share that after development of matrix mechanics and wave mechanics, Dirac generalized this theory as a Dirac in bracket notation. Okay, Dirac bracket notation, Dirac theory of quantum mechanics. So Dirac combinedly explained this matrix mechanics, wave mechanics in Dirac format. Dirac gave the general formalism of quantum mechanics, which is also any function is represented in terms of bra and cat and eigenvalue, that we will discuss in the next chapter. Okay, in 1928, what happened? Dirac taking combining the relativistic theory and quantum mechanics, Dirac proposed a new theory which is known as a Dirac theory. And this development of Dirac theory provide the establish the existence of negative particle. Dirac theory, two important consequences from Dirac theory, it tells the existence of negative particle. That is in 1928. Okay, so positron was theoretically developed in 1928, but experimentally developed 4 years later in 1932 by Anderson experiment. Okay, so Dirac theory also established the spin of particle, spin of electron, spin of particle. We will discuss in the Stern-Gerlach experiment. Discover spin of electron was introduced in 1925. So by two German scientists, Stern, and we can understand the nature why it is introduced in Stern-Gerlach experiment. So Dirac in 1928 provide Dirac theory, and combining relativistic and quantum mechanics, we will find different type of equation, KZ equation, Klein-Gordon equation for spin zero particle, Poca equation for spin one particle, Dirac equation for spin half particle. So this type of equation is developed in 1928, and this is what is the background of quantum mechanics, how quantum mechanics develop, and why quantum mechanics develop. What is the moral of the thing is that quantum mechanics is developed specifically to analyze the microscopic particle and nature of the microscopic particle that cannot be explained by the classical theory. So classical theory, the sum of experiment that cannot be explained by classical theory: one, photoelectric effect, black body radiation, pair production, okay, and Pacific heat of solid. These all experiments are unable to explain by the classical theory. And now, after development of this quantum theory, this theory enable us to analyze microscopic as well as macroscopic particle. This is how quantum mechanics has developed. And after this experiment, after this is the development of experiment, the formulation in the quantum formulation of quantum mechanics, they consider some postulate. Okay, postulate which is known as the postulate of quantum mechanics. The postulate of quantum mechanics does not have any physical theoretical background. Based on some experimental evidences, they observe, they formulate some postulate, and based on that postulate, some theory was developed. If this theory, but validation of postulate, whether postulates are correct or wrong, you cannot do directly. Once the quantum mechanical theory, which is developed based on quantum mechanical postulate, accurately explain the microscopic phenomenon, then this postulate is considered as a correct postulate. And it is also seen that quantum mechanical theory not accurately explain the phenomenon, but it will explain accurately in qualitative and quantitatively. That cannot be explained by the classical theory. And next class we will discuss from the postulate of quantum mechanics and operator Dirac representation. If you understand, so everything you will find in the chapter 1 of Zettili book. And chapter 2 and chapter 3 is very essential. I am going to discuss in the next class. If you understand this chapter 2 and chapter 3, then you can understand any part of quantum mechanics. Okay? We will also, after teaching chapter 2 and chapter 3, we are going for a numerical problem and what type of question often asked in the NET-GATE exam. We solve the problem. We will teach you the tricks how to study. This is basic part. Anyhow, you have to understand. Okay. Thank you.